Welcome to this explainer. Today, we're diving straight into one of the absolutely coolest magic tricks in all of organic chemistry, figuring out complex, 3D molecular shapes from flat, 1D NMR graphs. We're going to see exactly how chemists use chiral resolving agents and the Mosher method to lock down both relative and absolute configuration. If you've ever wondered how on earth we can see the exact 3D orientation of microscopic atoms using literally nothing but magnetic fields and radio waves, well, you are in the perfect place. So how do we actually do it? It's a literal detective story, mostly because standard NMR has a massive blind spot. It is completely blind to enantiomers. Think about it. If you toss a pure R enantiomer and a pure S enantiomer into a standard magnetic field, they are going to spit out perfectly identical spectra. In an achiral environment, their protons are processing at the exact same frequencies. For anyone trying to solve a structure, that is a huge roadblock. But this contrast right here is exactly what we exploit. Enantiomers are perfectly hidden from our instruments because their internal distances and magnetic environments are exact mirror images. They're identical to the machine. Diastereomers, though, totally different story. Because they aren't mirror images, the spatial distances between their atoms actually vary. That means their protons live in distinct magnetic environments, giving us completely different chemical shifts that we can actually measure and quantify. To really picture this, think of these chiral molecules as a pair of identical left and right gloves lying flat on a table. They take up the same space, they look the same. You can't tell which is which just by weighing them. You need a handed object, like your right hand, to interact with them. Your right hand slides perfectly into the right glove, but definitely not the left. It's the same in chemistry. We have to introduce a handed chemical environment to force these invisible enantiomers to reveal themselves. Okay, real quick, before we get to the heavy-hitting tools, we need to call out a bad habit. The source material refers to it as the lazy way out. When looking at complicated overlapping resonances, some chemists just label the peak a multiplet and move on. But doing that is literally throwing away a goldmine of data. Those intricate coupling constants, especially the differences between axial and equatorial interactions, are the exact keys to unlocking the 3D stereochemistry. We really have to look closer. All right, moving into section 1, the first clue, chiral resolving agents. This is where we create that handed environment we just talked about. So, this technique relies on a chiral resolving agent. Basically, it's an optically pure reagent that we intentionally mix and react with our racemic mixture. A classic example? Taking a mixture of R and S amines and reacting them with an optically pure acid like S plus O-acetyl mandelic acid. When they react, they form salts. But here is the magic part. We don't have enantiomers anymore. An R-amine with an S-acid and an S-amine with an S-acid, those form a pair of diastereomers. Just like that, the invisible becomes visible. And this is the big reveal right here. The actual spectrum literally splits right before our eyes. The methyl groups next to the chiral center in our new diastomers are now sitting in different magnetic environments. The R isomer salt shifts downfield, and the S isomer salt shifts upfield. Boom! We get two distinct doublets where there used to just be one messy overlapping signal. And since we now have these beautifully distinct signals for the R and S components, we can just run a simple integration on the spectrometer. The area under each doublet gives us the exact ratio of the mixture. It's an incredibly elegant and direct way to determine enantiomeric excess, relying entirely on just solid stereochemical logic rather than crazy expensive new machinery. But what happens if we need the absolute configuration of a completely unknown sample? That brings us to section 2, the ultimate tool, the Mosher method. This is basically our CSI enhance moment of the explainer. The absolute star here is the Mosher reagent, or MTPA. Now watch out for this, because there is a notorious trap for the unwary chemist here. If you convert the MTPA acid into an acid chloride to make it more reactive, well, the physical 3D shape of the molecule doesn't change at all. But because chlorine has a higher atomic number than oxygen, the Kahn-Ingold-Prelog priority rules totally flip, so the R acid suddenly becomes the S acid chloride. It's this wild little naming quirk that has caused so many headaches and incorrect assignments over the years. So, keeping that naming quirk in mind, how do we actually do it? It comes down to these 3 steps. First, take your unknown alcohol. React half of it with the R Mosher reagent and the other half with the S Mosher reagent. Second, you run NMR spectra for both of those new diastereomeric esters. And third, you just do the math. calculate the difference in chemical shifts between the two spectra, which gives us a value we call delta SR. So why does this little math trick work? It all comes down to the molecule's preferred conformation and the phenyl ring acting like a giant magnetic umbrella. Mosher figured out that when the molecule locks into its preferred coplanar geometry, that big phenyl group casts a magnetic shadow, a shielding effect. In the R-MTPA ester, the umbrella shields the L2 position. In the S-MTPA ester, the geometry flips, and the umbrella shields the L1 position instead. The math basically finishes the detective work for us. We subtract the chemical shifts of the R ester from the S ester and look at the sign of our delta SR value. Is it positive? That means the protons were heavily shielded in the R ester, so they sit at the L2 position. Negative? Shielded in the S ester, placing them at L1. By mapping out those positive and negative values, we can draw out the exact 3D absolute configuration. It's brilliant. Now, Mosher's reagent might be the most famous, but other chiral derivatizing reagents work great too, as long as they follow these 3 rules. 1, they have to solidly attach to the unknown substrate, usually covalently. 2, they need a bulky or superpolar group to stop free rotation and lock the molecule shape into place. And 3, they need an anisotropic group, like our phenyl ring, to cast that strong magnetic shadow and force the diastereomers to reveal their spatial differences. Okay, on to section 3, falling action, finding relative configuration. We've got the absolute handedness of a single chiral center figured out, but how do we see how multiple substituents sit relative to each other across a big flappy carbon chain? For this, we have to talk about the incredible carbon-13 acetonide method popularized by chemist Scott Rajknovsky. See, acyclic 1,3 diols are notoriously floppy. They rotate freely, so it's nearly impossible to tell if the OH groups are pointing the same way or opposite ways. Rajknovsky's genius move was to react them with acetone. This locks the floppy chain into a rigid 6-membered ring called an acetonide. From there, carbon-13 NMR does all the heavy lifting. Because the new ring is rigid, the NMR results are just wonderfully predictable. If your original diol had its OH groups on the same side, a syn diol, the ring forms a stable chair conformation. That gives us 2 distinct carbon peaks right at 19 and 30 parts per million. But if they were anti, pointing in opposite directions, forming a chair would cause a massive unstable steric clash, so the molecule twists itself into a twist boat conformation to survive. That leaves both methyl groups in identical magnetic environments, and they pop up symmetrically, exactly at 25 ppm. You know, the source material has this fantastic analogy. The NMR spectrometer is essentially a camera with a really slow shutter speed. Because these molecules are tumbling around millions of times a second, NMR is just capturing an average picture of that blur. But by cleverly locking these molecules down using chiral agents or acetonides, we are basically telling them to hold a pose for the camera, letting us see exactly what they look like in 3D. The way we can manipulate a molecule's shape just to exploit its magnetic environment is nothing short of incredible. And it really leaves you wondering, if a clever chemical reaction, a locked ring, and a simple magnet can definitively map out these entirely invisible 3D universes, what else is out there in the microscopic world just waiting to be uncovered? Thanks so much for joining me on this explainer, and keep questioning what you can't see.